the on-off buttons for them.
Okay, hi everyone, welcome. Our next press conference is Defending the Home Planet. Our four participants are Joseph Nuth, Robert Weaver, Catherine Plesko, and Galen Gisler.
All right. Planetary Defense. I'm the one that goes first, so I give a little bit of context and then recommendation. My talk is about comets, basically. Comets, over the 5,000 years of human civilization, really weren't anything but nice, pretty lights in the sky. At worst, they were portents of doom. Nobody really considered them the catastrophe itself. That is until Alvarez et al. Basically suggested that a comet or an asteroid impact could wipe out the various species on the surface of the Earth. A lot of work has been done since that time, and one of the recommendations that came out of the work following the Alvarez paper had been to look for and catalog all of the asteroids that might be a problem. When this effort started, there were about 5,000 asteroids. We find a couple more each night, but there are more than 700,000 asteroids known at the moment. And that number is building. On top of this, NASA has established a planetary protection office, basically a planetary defense office, rather. And that actually has led to looking at sponsoring a couple of tests of methods that might be used to deflect asteroids. That's more the politics right now than the feasibility. We can certainly do these tests, and it will tell us a lot about what we can do to mitigate an asteroid threat. On the other hand, comets have largely been ignored by people that are interested in defending the planet. And there's a lot of reason for it, but the biggest problem basically is that there's not a hell of a lot we can do about it at the moment. If you look at Siding Spring as an example, and I will remind you that in '96 we actually had a close encounter with a comet as well, and that was Shoemaker-Levy 9 that impacted Jupiter. So this is the second one in a couple of decades that has had a close interaction with a planet. And the specific thing to know about this is in January 2013, it was discovered, comet Siding Spring, and in October of 2014, only 22 months later, it passed basically within cosmic spitting distance of Mars. Total time, 22 months. If you look at the schedule for producing high reliability spacecraft and launching them, it takes 5 years to launch a spacecraft. 5 years. We had 22 months of total warning from the time you detected it until it was at closest approach. So it's really imperative that we reduce that reaction time. And the recommendation that my co-authors and I made was that we need to do that by building an interceptor and putting it into storage and periodically testing it. We also need to build a simple observer spacecraft, put it into storage. We would launch the observer spacecraft on warning, and that would allow us to maximize the effectiveness of the interceptor and would also refine the comet's orbit. And we would launch the interceptor only at the time when we knew that there was a predefined level of certainty of the impact. The rationale for the recommendation is that an observer can document a comet's shape, spin axis, the rotation state. In other words, it tells us where we're going to be most effective in hitting it in order to have the maximum effect and the maximum probability of deflecting that comet from impacting the Earth. An observer can also provide a very accurate position for at least one point in the comet's orbit. Building a high reliability spacecraft is hard. It takes a long time. We can cut that 5-year schedule in half, and it cuts down the probability that it will be an effective launch. We can cut it into a quarter, and that's basically a Hail Mary pass. So if we build it on a normal schedule and put that interceptor into storage, we can launch it in less than a year. That might actually be what we need to do. It reduces the launch time by about 4 years. And I will conclude by basically also saying that this could mitigate the possibility of a sneaky asteroid coming in from a place that is hard to observe, like towards the sun. We could also use this interceptor on an asteroid as well as a comet. And that's pretty much it. Thank you.
So I'm going to go old school and just talk. Good afternoon. My name is Bob Weaver. I'm the point of contact for Los Alamos National Laboratory for our team working on planetary defense. I'll give a brief introduction of the aspects of the project that we're working on, and introduce the two other panel members, Kathy Plesko, who's been working with us for a very long time, and I've been working with Galen Gisler for close to 2 decades now. We have an additional member of our team, Tamara Heberling, who gave a very nice talk this morning in the session this morning. And so we have a dedicated team of people that is focused on working the issues for this topic. We're studying 2 important mitigation techniques, one kinetic impactor simulations, and the other is nuclear explosive simulations. Both Livermore Laboratory and Los Alamos Laboratory are in a key position to help with the nuclear explosive deflection technology because of our workload in that area. We also work very strongly with Sandia National Laboratory. So there's 3 national laboratories for the U.S. government that have been tapped into, and we collaborate on a routine basis with both of those laboratories. And in fact, that forms a great part of what we call the peer review process that ensures that the work that we put out is of the best quality. As I said, there's 2 important aspects. There's a kinetic impactor mitigation philosophy, and there's a technique, and there's also a nuclear explosive technique. The kinetic impactor technique can be very, very effective if you have long enough lead time. It imparts a momentum to the asteroid in addition to additional gain momentum from what we call the beta factor, additional mass that's blown off, and can be very effective if you have a long enough lead time, decades to centuries. If in fact the lead time is extremely short, there really is only one option left, and that's a nuclear explosive. And that's because the nuclear explosive encompasses the largest amount of energy and the smallest amount of deliverable mass, and is an extremely effective method for both deflection, and if it's a last minute thing, we can actually disrupt the entire asteroid, given its size. So there's 3 main aspects to what choice goes into a deflection mission. One is the lead time, one is the size of the object, and the other is what is the composition of the object. Quite honestly, we really don't know the composition for a potential hazardous object, and so that has to be played into our scenarios as we study the problem. Ultimately, the choice of the mitigation techniques depends on the available lead time after a decision has been made at an international or national level to actually go forward with a mission. That decision process is based upon the probability of that asteroid actually intercepting the Earth. When an asteroid is first put on the PHO list, the probability of intercept is usually very, very small. After repeated orbits and observations of that asteroid, the orbit is more well defined. The probability of impact usually goes away, but could be increased. And on subsequent observations, if the probability of impact actually approaches a significant value, that's the point that the national decision makers will likely make a decision, but that also shortens the lead time to where we actually can put together a mission. And this feeds very nicely into what Joe just said, is wouldn't it be nice to have a planning stage without a rush where we can actually have something put in place and have it available. So what I'd like to leave off with is the talk from Tamara this morning was on a kinetic impactor solution. Galen Gisler has worked on a variety of kinetic impactor simulations. We use physics-based codes, hydrocodes, and in some cases what we call radiation hydrocodes. For a nuclear blast, a majority of the output of the energy of a nuclear explosive is in the form of X-rays, and therefore we need to properly simulate that with what we call a radiation hydrodynamics code that involves not only hydrodynamics, but transport of the radiation energy field. And these are one of the strong points that we have at the national laboratories. And so we're exploring both kinetic energy impact, deflection mechanisms, nuclear explosive deflection mechanisms, particularly in a standoff burst mode. And the third aspect of the work that we're doing, and Galen's going to represent this today, is what happens to the Earth and to the population of the Earth should a PHO, a potentially hazardous object, not be intercepted, or the choice be made not to intercept it. What are the consequences of that? Galen's going to be talking particularly about the largest mass of the Earth is covered by oceans, and what happens if an impact comes in and either has an airburst over an ocean or has a direct impact over the ocean. Thank you.
Hi, I'm Kathy Plesko. I work for Bob, and I am a little more of a visual thinker, so I'm going to pull up some pictures here to show you today. Let's see, there we go. Oh, there we are. Okay. And let's go big. And there we go. All right. So specifically, I'm going to give you a little more detail about nuclear deflection. As Bob said, we have two ways of preventing an impact that we're talking about, that we're thinking about and modeling. The first one is kinetic impactor, which is basically a giant cannonball. And cannonball technology is actually very good technology because you're intercepting the object at very high speed, and so it ends up being more effective than using conventional high explosives. If you really need a lot of energy, though, a nuclear burst is the way to get the largest amount of energy out to the object in the smallest possible container. And so we are very carefully doing our homework before finals week, so to speak. If you look at life as an academic class, then we don't want to be doing our calculations when we know something is coming, and that's, to me, that's finals week. When we don't have any more time to study, we need to make a decision and go forward. We need to have this work done. So here is what we're talking about with a nuclear burst. So if we have the Earth's orbit, I do have a pointer. Here's the Earth's orbit in blue. It's approximately circular around the sun. We have objects, potentially hazardous objects, that come in at much more elliptical orbits. If it's a comet, it might even be hyperbolic, coming in the third dimension, which would be into the page there. But either way, PHO's orbit intercepts the Earth's orbit, and if we're having a very bad day, it intercepts at a place where the Earth is going to be on that day. And so if we want to prevent an impact, then we have to either speed it up or slow it down in its orbit, the smaller object, or blow it to smithereens. But that takes a lot of energy, and then you have shrapnel you have to track. So we're really hoping for, at least with the smaller, more frequently found things, that you can push it in its orbit and not have to disassemble it. So here's what we would do with a standoff nuclear burst. If we detonate up here at some height above the object, then it heats the surface, and then the recoil of the vaporized material coming off then pushes it along in its orbit. And this is a shape model of asteroid Bennu, which is the target of the OSIRIS-REx mission, which is not currently thought to hit Earth, although it is potentially hazardous. It has a 1 in about 2,000 chance of hitting the Earth about 200 years from now. And so that's one of the ones that we're studying, and we'll have a paper coming out with NASA on our results for that in a couple months. The way we study this is using computer models, as Bob said, hydrocodes or radiation hydrocodes. And what that means is we take the equations that model fluid flow. And we put those into a computer, and then we add in equations that model material responses, so boiling points, melting points of different materials, densities, things like that, phase changes. And then we add to that the equations that model light moving through a medium. So Maxwell's equations, if you've ever seen the t-shirt that says, and God said, and then like 5 lines of calculus, and then there was light, those equations. And so we put all of those into a code, and then we can import shape models of the situation we want to model and let it go forward in time and explore what would happen. And the more physics we can put in, the higher fidelity we can do these models at. This is what we're doing on the giant supercomputers that we have at Los Alamos and Livermore and the other labs. This is why we need bigger, faster computers, is to do these calculations with the best accuracy and the most complete physics that we can. For an example, here's something I did for my thesis where I was modeling an experiment that was done where they had basically an artillery gun firing copper slugs into plates of basalt that had pressure sensors between it. And that was done by Nakazawa et al. In Japan. And so I took the results from their paper and their models, so their engineering drawings, and then I mocked it up in our computer and let her rip and watched in blue there, the Smurf colored one is the shock is coming through after the bullet has hit the first plate. You can see it's even slamming through partway, and you can see the shock propagating through the pressure sensors that I've cut back the basalt plate so you can see the pressure sensors there. And that's one of the other advantages of using hydrocodes is we can zoom in, we can look at different variables, we can look at time, resolution, we can cut something in half and look inside of it and really explore exactly what's going on. And the nice thing is when I'm done with one of my numerical experiments and I need to clean up, I hit delete. So it's much simpler than doing, and much less expensive than doing a full-scale experiment. And for some things like studying nuclear deflection, it really is the best idea to do an intensive load of these calculations before we even need to contemplate doing anything real. So that's a hydrocode, and that's what we're doing. Here is a model that Bob ran the calculation, and this is based on a shape model of asteroid Itokawa, and I filled that through full of little ping pong balls of rock of various sizes. It's a mathematical model of rock, so the density and the phase changes are correct. And then Bob put down at the point there a ball of energy, about a megaton, and then we let that propagate forward in time. It explodes. You're seeing the fireball coming off, and you're seeing the shock propagating through the different boulders there, and as the boulders contact each other, then the shock propagates through and it weaves its way through the asteroid. I'll refer you to the Los Alamos National Laboratory's YouTube channel where you can see this in an animation. It's really cool. And we also have several others, including the animation that Galen's going to talk about. So this is a peek at how we're filling in the details. These are the calculations and how we do them that feed into the results and the suggestions that we hope to someday be able to provide to NASA and our national policymakers. So thank you for your time.
So as Bob said, I'm going to be talking a little bit about what would happen if, where is mine? Oh yeah, there it is. Oh, there it is. No, come on. I don't understand this computer. I just keep, there we go, right, okay. Yeah, what my concern is what will happen if we are not able to deflect an asteroid and right. So I'm not the only one who can't do this. Right. I keep pulling up these blank ones.
Oh, I think you closed it.
Right. Where are we? There we go. There we go. Okay, thanks. What I've been working on the question of what happens when asteroids hit the ocean for a number of years, and in this this past year I've been specifically focused on oblique impacts, which have to be done with three-dimensional calculations. The results we had a meeting in Seattle a few months ago and presented the material here. The results of the impacts of small asteroids, that is less than 300 meters in diameter, are as follows. First, an impact or an airburst near a populated shore will be highly dangerous. Likewise, an airburst over a city on land will be highly dangerous. We saw that in Chelyabinsk, which fortunately didn't kill anyone, but it could have been a lot worse. Impacts that occur far from shore, which is of course the most of the oceans, they're big and there's lots of area that's far from shores. They're spectacular, and they may produce detectable waves, but not necessarily tsunamis. And again, I'm talking about small asteroids, the most common asteroids, less than 300 meters. Airbursts over water are less effective at generating waves than impacts into water. So you really have to make a splash in the water rather than just a pressure wave above the water in order to make waves. And finally, the most significant effect of an impact into an ocean is the injection of water vapor into the stratosphere. Now, water vapor, when it's in the troposphere, it rains out pretty quickly. Water vapor in the stratosphere can stay there for a good long time, and so you might have climate effects. So this animation shows the impact of a 250-meter asteroid into a deep ocean, and of course the first thing you see is this enormous splash that goes up tens of kilometers into the air, and then it produces a crater, and then that crater, as it fills, produces a jet that runs up a kilometer or so into the air, and as it collapses, you get a rim wave, and that's the beginning of a wave that might propagate out into the open ocean. The rim wave is, in many cases, several hundred meters high, but because it's a point source, unlike a tsunami, which is generally a line source, it decays much more rapidly than tsunamis from earthquakes, undersea earthquakes, or from landslides. And I'll play that one again just because it's so much fun. Whoops. Here's here's another one. So, can we? Yeah. Okay. Play that one again. Here. So you get this splash, and you also see this big pressure wave that goes out in all directions. It vanishes pretty quickly, and then you get this crown splash, followed by the crater refilling jet in the middle. This is just like when you throw a rock into a pond, right? And then a big rock, and then you get this rim wave from the collapse of that jet that propagates on out. Right. So here's an image of a city. In fact, some of you might recognize the city. It's Seattle. This is Seattle, of course, is well protected by Puget Sound and all the islands and stuff like that. So this isn't entirely realistic. But the point that I'm making here is that you really don't want to be close to an impact site because in the first instance, the effects of... Why did that do that? Whoops. I don't know. This is not, these things are very large compared to the profile of a city, and so things could be very disastrous if you happen to live very close to an impact site. So an impact that occurs close to shore is going to be really dangerous. So here's an animation showing some more of the physics of the situation. Down in the bottom is pressure, and up at the top is water mass fraction. And you see what's happening down here. This looks very much, it's very reminiscent of the kind of fireball expansion that you have in a nuclear explosion or an explosion of any kind. And the reason for that is that the dissipation of the asteroid's kinetic energy when it hits the water. I mean, you have this object coming in at Mach 72 or something like that. It hits the water. it just dissipates all of its energy at once, and so that's an explosion. And that explosion results in this fireball type feature. You also get this plume feature, which is basically the evacuated channel as the asteroid comes into the water, and the evacuation of that channel sucks a lot of stuff, both asteroid material, water vapor, and atmosphere up into space, going out that way. Eventually, as that channel fills up, then you just get buoyant motion of the water vapor up into the stratosphere. And here's a comparison of three different Okay, on my keynote, those things all run at once. This is a complaint against PowerPoint. But, right. Yeah, okay. Sorry, that was a rant, an uncalled for rant. So the top one is just an impact, no airburst. Perhaps the second one will run next, or maybe not. Yeah, and the second and the third go at once. So, and then these two are airbursts, one at 5 kilometers altitude, the other one at 10 kilometers altitude. And you can see as this thing has gone on that the impact on the water is considerably less when there is an airburst, and that's basically because all of the asteroid has basically blown itself apart because of the airburst, and so there's less stuff to come down into the water. And so all you have, the effect on the water, especially if the airburst is higher, like 10 kilometers, is the overpressure from the explosion. At 5 kilometers, you do get something of a crater with a little jet coming up and a wave producing from that. But 5 kilometers is very low for an airburst to occur. The one at Chelyabinsk was what was it, Mark? 30 kilometers up or something like that. And Tunguska, similarly. We expect airbursts to be a lot higher than this. And so the effect would be correspondingly less. As far as size, if you have a 100-meter asteroid as opposed to a 250-meter diameter asteroid and subject them both to an airburst at 5 kilometers, what happens is that basically nothing arrives at the surface from the smaller guy, and you get something arriving at the surface from the larger guy. The smaller guys, of course, are much more common in our neighborhood. So there, and I don't know, that should have not. Anyway, PowerPoint. So, and then here's just single frames from 100-meter asteroid with no airburst, 250 with an airburst, and then the 100-meter and 250-meter with a 5-kilometer airburst. And you can see the difference. It's basically the worst effect is when you have a big guy that actually hits the water, if the airburst considerably mitigates the effect on the water. And here's looking at the water surface after the jet has collapsed. And then here's looking down at the water surface, and here a slice through it. You see the waves are breaking. And they're also, the wavelength there that you see is like 5 kilometers. It's basically about the same as the depth of the ocean. That's in contrast to a tsunami that results from an earthquake or an underwater landslide, where the wavelengths are 100 kilometers long or so. And so the wavelengths are much shorter. These are not proper shallow water waves. They don't propagate as efficiently over long distances as waves from earthquakes or landslides. And in the case where you have an airburst, the effect is considerably mitigated, but you still get breaking waves, and the wavelengths are still fairly short. I'll end with this animation, which is just revolving around and showing some of the asteroid material too, but it's very similar to the one that I first showed. And I think with that, the panel here is ready to take questions.
Okay, do we have questions from reporters in the room? And just state your name and affiliation.
Hi, I'm Deborah Werner from Space News. What would have to happen to enable you to get a mission ready? What are the steps between here and there?
Congressional approval is the biggest one. You would have to have NASA
First
basically.
request.
Excuse me?
They have to request.
NASA would have to request the mission, and then the mission would have to be approved. Would be a specific line item in the congressional budget. So this would have to be something that is basically probably a couple of years in the political process before we'd even start.
Do you have advocates for that, or is this just the beginning of a campaign to move in that direction?
This is just the beginning from our point of view.
Mm-hmm.
Any other questions from reporters in the room? Yep.
Hi, Irene Klotz with Seeker. For Dr. Nuth, you mentioned that you have this recommendation, so could you say who that's for or where that went and what's going to happen with that?
All right. It is for, right now, basically anyone who will listen. I'm a NASA scientist. I'm not a NASA policymaker. I'm not even in the administration of NASA. So this is more a scientific recommendation based on comparison of what it takes to actually launch a high reliability mission. And frankly, if I really had to push this, I would have a backup as well. So you're talking a considerable amount of money in terms of the request. The NASA request would probably be for several $100 million to produce one of these spacecraft. And then it would be stored, and that storage could last years. We do fortunately have an example. The Triana spacecraft that was put together was in storage for 2 decades before we launched it as Discover, and seems to work fine. So there's no real problem with building it and putting it into storage. That's much better an alternative as far as I'm concerned than trying to build it in a quarter of the time where you don't have time for tests and other things. So NASA has just established a Planetary Defense office. Maybe they will take this up and advocate it. I can't tell. Like I said, that's above my pay grade.
Hi, this is for Galen. I was hoping you could talk a little about how impacts over sea compare with impacts over land in terms of just their severity and the potential for human impact.
Right. So in a study that was done 15 years ago or so, it was considered that the largest risk was associated with impacts over sea simply because the seas were, the largest part of the Earth's surface, 70% or something of the Earth's surface, and that there was a potential of generating waves that could propagate very long distances, so that an impact anywhere in the ocean would affect anyone along the coastline. I've long been skeptical of that point of view, and lately the studies that I've done and other people have done have suggested that really an impact over the ocean is not as dangerous, mainly because it's very hard to produce a tsunami from an impact, being a point source and generally being much smaller than the depth of the ocean, and so forth. Impacts, as I said, impacts close to shore are dangerous, and they're, from that point of view, they're just as dangerous as impacts on land near population centers. I mean, if you have an impact in the middle of the Sahara, it is not. I mean, the hazard associated is going to be less than if you had an impact over London. The real question, with impacts of the size that we're considering, which is in the range less than about 500-meter diameter, is where exactly on Earth is that impact going to take place? And so then this feeds into then the question of defense against an asteroid. You want to know not only that it's going to, that it has a high probability of hitting the Earth, but also where. And if you defend against something, you want to be certain that you're pushing it in the right direction and not making the event more hazardous by pushing it inadvertently over a large population center. So, I mean, we're focusing on small asteroids because they're the most frequent, and also because NASA has done an extremely good job in detecting and characterizing asteroids that are greater than 1 kilometer in size. And gradually, as the observations improve and more observations are made, we're pushing that limit down to lower and lower asteroids. And the question is, just how low do we need to go to be completely secure? And so we're focusing now on the small diameter ones. And the message that I'm arriving at is that the small impacts over ocean are not necessarily a threat to us unless they occur close to a center of population.
Are you aware of U.S.A. or any other non-U.S. agency working on something like this? And if not, are there any scientists from non-U.S. organizations collaborating with you? Oh, Rick Myslewski from the Register, sorry.
Yes, absolutely. We are, one of the things we do every couple of years is attend these international planetary defense conferences. The next one will be in Tokyo in this coming May. You're all invited, by the way. And the last one was in Frascati, Italy. Before that, Bucharest, Granada, and Flagstaff. I mean, these happen every couple of years, and only one in the recent decade has been in the United States. So yes, there are literally thousands of scientists all over the world working on this problem, both on the consequence side and on the deflection side. The mission, the AIDA mission, which involves both NASA and ESA components, is one example of a very tight collaboration that we hope will be ongoing until that mission eventually happens. But yes, there are certainly collaborations ongoing. We talk to our international counterparts about this all the time.
Hi, I'm Rebecca Boyle. I'm freelance. I'm wondering what difference it would make, or what we would prefer for an observatory in space versus something on the ground. Like, what benefit do you get from looking for near-Earth objects from space versus what we can do now on the ground? And should we prioritize ground-based observatories? Can they do a good job of this, or do we really just need to go to space?
Okay. Ground-based observatories do a great job for most of space. The real problem is that there are just a few angles that are hard to see, basically, depending on where you can locate your observatory. The problem with space-based observatories, of course, is they're expensive, and there's no maintenance. There's no really good way to maintain them. But on the other hand, for instance, they can look in the infrared so that you can get a very good handle on what the size of the body happens to be, as well as detecting it. The NEOWISE mission, for instance, did a good job of detecting and characterizing asteroids in space. But the vast majority of asteroids have been basically detected, and their orbits have been characterized quite nicely by the ground-based observatory systems that the NASA has funded.
Okay, I believe we have a question from the web chat.
We have a question from Kelly Beatty at Sky and Telescope. This question is for Dr. Plesko. Kelly asks, can you model different asteroid or comet interiors, for example, loose versus compact interiors, and how they respond differently to impacts? If so, how do the results of that modeling differ?
Well, Kelly, yes, we can, and we do put a lot of work into that. One of the gotchas is we don't have a lot of data about what the insides of comets and asteroids look like. That would come from radars or seismic thumpers, things like that, that would have to go there. So we don't know a lot of what's going on inside, but based on what we know about physics and rocks and ice, we can guess, and we can put in voids, we can model porous materials. There are specific mathematical ways of doing that, and so we study how to do that. We can also do small-scale experiments where we send a shock wave through a small sample of a porous material and ice, or some rock dust. I've worked with the NASA lunar and Martian simulant soils that are actually Earth soils but look like moon dust or look like Mars dust. and we send a shock wave through that and watch what happens, and then feed the model into the computer and say, okay, can I get the shock to come out the other side of the sample at the time it's supposed to? Does it crush up to the right density? Does it get to the right temperature? Things like that. So yes, we do check our numbers very carefully against that. And then we have other people model these things with different codes to say, okay, let's check each other's math and let's each try to solve the same problem a different way and see if we get to the same answer. And so that's part of the collaboration that we have with NASA and with Livermore and Sandia, is to, okay, let's each of us run our own model, our own code, and make sure that we get to the same numbers.
Jennifer Lehman from the Science Day from the California Academy of Sciences. Do we have an idea about what sort of lead time we would have in terms of being able to tell whether or not something could impact at an angle, or whether or not it would be prone to an airburst? Are there certain types of objects that are more prone to airbursts? I suppose that's kind of piggybacking on that question. Thank you.
So, if an object is very porous and weak, then the interaction with the atmosphere is more likely to cause it to burst. If an object is like the iron meteorite that made Barringer Crater in Arizona 50,000 years ago, that the high density, very strong material came all the way to the ground. Maybe it fluffed off some stuff while it was coming down. Nobody was there to watch it, but basically it depends on the strength and porosity, the material characteristics of the asteroid, which, as Kathy indicated, we really don't know for most of these objects. You would, if you see something out there that's a threat and it's coming towards the Earth, you would really have to fly something that lands on it, to characterize its internal structure before you really know whether it's going to be an airburst or not. In some cases, you can measure the mass, which will tell you something, given the albedo and the diameter and so forth. But in most cases, we really don't know. We really would not know before it's too late, whether it was going to burst or come all the way to the ground. Smaller objects are more likely to burst, of course. Bigger objects, less likely. Stronger objects, less likely. Weaker objects, more likely.
But we don't necessarily need to know the interior in order to mount a deflection attempt against it. If we're using, for example, a nuclear standoff burst, then you're just heating the surface in a very thin layer and then blowing material off. And even with a kinetic cannonball impactor, yes, the shock does go all the way through, especially if it's a smaller sub-kilometer scale object, but the crater you're making is close to the surface, and the ejecta you're throwing off, which actually is what does the momentum transfer, is primarily a surface process.
David Kramer, Physics Today. Has anyone done a probability estimate of an asteroid of a certain size, say, I don't know, a kilometer in diameter, hitting the Earth over a given time? And is that calculation changing in recent years at all?
Do you want to cover the surveys?
The answer is that yes, many people have actually done those calculations, and they've been doing them for the last couple of decades. The probability of being hit by small things is obviously much larger than the probability of being hit by large things. There's been basically just because there are so few large things in essence, but on the other hand, they are the extinction level type events, and that's especially true for things like comets. The numbers are Monte Carlo and almost anybody's guess. When you're talking about things like dinosaur killers, they're 50, 60 million years apart, potentially. You could say, of course, we're due, but it's a random guess. At that point, you can do a lot of modeling, but it's being in the right place at the wrong time.
Yeah, I would add Al Harris has done a lot of these calculations of probabilities of impact and so forth, and the numbers do change based on new observations of the numbers fortunately, the probabilities seem to have been going down to some extent over the last couple of decades. But he keeps pretty close tabs on this, and I think other people do too. So, yeah, this is these calculations are done.
Okay, do we have any other questions? Yeah.
Hi, Lauren Summer with KQED Public Radio. Could you just describe a little bit more, if you had a nuclear detonation, what the actual physical process is that you want to see? Is it just that you want to eject material off of it, or what's actually doing the work, the important work?
So the basic scenario with a nuclear explosion in standoff mode, as I said in my intro, most of the energy that's generated in a nuclear explosion is in the form of X-rays. And those X-rays transport to the visible surface of the asteroid, depending on what the orientation of the explosion is. Those X-rays are then absorbed in a very, very thin layer because of the opacity of the material in the asteroid. That heats up that surface, heats it up to such temperatures that it becomes vapor. It blows off the surface. And that vapor that blows off represents a momentum that's leaving the asteroid, and the counterforce from that then gives a push to the asteroid, and then deflects it in the opposite direction, and that's the deflection velocity that we're looking for to push it on an orbit that does not cross the Earth.
Okay, do we have any other questions from reporters in the room? Do we have any questions in the chat? Okay, then this concludes our press conference, and we'll resume at 4 p.m.